In the last video, I spoke about Faraday's law, and we learned that volt or a current can be induced on a wire, and this can be done by changing the magnetic field that a wire loop is experiencing, or also the area of the wire loop over time. And it's also relative to n, the number of loops. And again, you don't have to calculate this, but you just have to understand it conceptually. So there is a practical application for this idea, and it's how a generator works. So let's say I have a uniform magnetic field. Remember, we draw magnetic field lines with X's or dots if they're coming into or out of the page. Let's just go ahead and do this. So this would be our magnetic field lines going straight into the page or running perpendicular to the page. Now, if I were to take a metal loop and put it into the magnetic field, if I just set it there, right, it's not experiencing any current because it requires a change in the strength of the magnetic field or the area of the loop that is experiencing the field. If you notice then, let's go ahead and take this loop and let's turn it on its side. So as we start to spin it, you can see that the area that you can see or the field lines are going through gets smaller and smaller and smaller until it's nothing right here on its side. So see how as I turn the loop, the area of the loop that you can see, which imagine that your eyes are the magnetic field lines, gets smaller and smaller and smaller. So that would cause a change in the area, which would induce the current on the wire. Now, if we look here and let's continue our spin, now we can see the area gets bigger and bigger and bigger that we can see with our eyes until we get the whole circle of the loop again. And if we were to continue spinning this, we would essentially get small area and then large, and then small and then large. And this is how a generator works. We spin a loop in a magnetic field. So we're taking some mechanical energy, the energy that it takes to spin, and we're converting it to some electrical energy. Now, as a result of this spinning, we actually create an alternating current. As the size of the loop gets smaller, the current goes in one direction, and then as it increases, it reverses and goes in the opposite direction. So essentially on this loop, as it spins through, we end up with a current this way and 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 this way. Right? So that's how we create an AC current on this loop. Right? Now I'm going to show you another example using a simulation where we're converting some sort of mechanical power to electrical power by using this whole generator idea or Faraday's law. So let's go ahead and look at this simulation. All right. So here we've got a loop and we have the light bulb that will show us the current. And if I were to turn on, right now this is not experiencing any changing magnetic field. There's a magnetic field because this magnet is sitting close to it. However, there's no current because it has to change the magnetic field. If I were to rotate this magnet, then the strength of the magnetic field that this wire is experiencing would change, and therefore it would light up the light bulb. So here we start to run the water and we move the magnet, which causes a current. And because I am exposing both the south and then the north end of the magnet, you can see that it induces a alternating current. Now if we were to increase the rate at which this happens, you'd see we'd make more electricity. We could also increase the number of loops, and as I do that, it gets brighter and brighter and brighter. Okay, so this is another example of using mechanical energy, so falling water, just like a dam does, in order to generate some electrical power. So this is how a generator works.